Previously, we have defined the notion of transversality. In this video, we want to look at some examples and some special cases. So let us first quickly review the definition. The setup is that we have a smooth map F from a manifold M to a manifold N, and then inside N we have a regular submanifold Z. We say that F is transversal to this submanifold Z if the following condition hold. For every point P in the preimage of Z, we can look at the tangent space, right, to M at P, TPM. Okay. Now at the image FP of P in N, we can look at two different tangent spaces. So the tangent space to N at FP, and then we also have the tangent space to Z at FP. Now this map F induces a map on tangent spaces. So let's say the image of TPM under this differential, this derivative dpf is this line here. Again, I'm drawing it as a line, but that doesn't mean it's actually one-dimensional. Now, so what does it mean for F to be transversal to Z? Well, F is transversal to Z if this black line and this blue line together generate this plane that I drew here. In other words, if the tangent space to N at Fp is generated by the following two subspaces. One is the image of this derivative dpf, and the other one is the tangent space to Z at Fp. If that condition holds for every point P in this preimage of Z, then we say that F is transversal to Z. So that was a bit of a mouthful. Now let's look at some concrete examples to have some intuition. We'll start with examples of two maps from the real line to the plane. In both of these cases, we will let Z be just the x-coordinate on the plane. The prototypical example of a regular submanifold. So our first smooth map is given by T maps to T comma T square. In other words, it maps the real line to this parabola, which is y equals to x squared. We claim that this is not transversal, and let's see why. So let's take P to be the origin, right? The image of the origin is still the origin. Let's show that this equality does not hold here. Okay, so first, what is the image of the tangent space of the origin? Okay, so first let's identify the tangent space to this origin in the plane as the plane itself. Then with that identification, what is the image of the tangent space here to R at the origin? Well, that's going to be this x-axis. Now what's the image to Z at the origin? It's also still going to be this x-axis. So together, these two subspaces of this tangent space do not generate the full tangent space. And so we see that the map is not transversal to this x-axis. So now let's look at another map from the real line to the plane. This is given by T map to 0, T. So it just basically sends the real line to this y-axis. Now the preimage of this Z, the x-axis, is just the origin. So to check transversality, we just need to check that this condition holds at the origin. So let's check that. Now the image of the origin is again the origin. What's the image of the tangent space to the origin? Well, it's gonna be this line, right? And now what's the tangent space to Z at the origin? Well, it's gonna be this line. So together, they actually generate the tangent space to the plane at the origin. And thus, in this case, we have Z is transversal to this F. So from these two examples, we have some intuition about the transversality. In this case here, this is not transversal because the image of F and Z share some common tangent direction. Right? Somehow this captures the idea of intersection multiplicity. Whereas in this case, the image of F and Z, they do not share any common tangent directions. So no tangent direction go wasted. And that's the idea of transversality. Now, to conclude, we want to look at two more examples of transversality. These are special cases that we mentioned in the motivation video. The first special case is when z is just a point. Let's call it q. Now, in that case, the tangent space to q at q, that's just 0. So this transversality condition just says that the image of this tangent space, TPM, right in here, should actually be the whole tangent space to n at q. In other words, this map, this derivative should be surjective, right? This derivative at p should be surjective. In other words, f is a submersion at p for every point p in the pre-image of q. So that means that q is a regular value. So in the special case, when z is just a point q, saying that f is transversal to z is just equivalent to saying that q is a regular value of f. And thus, as we've mentioned, transversality is a generalization of regular value. Now, the second case is when f is just an inclusion map. So then, in that case, the pre-image of z under the inclusion map is just the intersection of m with z. And so this transversality condition is just saying that for every point p in this intersection, the tangent space to m at p, this black line, and the tangent space to z at p should together generate the tangent space to n at p. In this picture here, we see that indeed z is transversal to the inclusion map, but let's look at this picture here. In this picture, z is not transversal to the inclusion map, because let's look, this is the tangent space to m at p, and this is the tangent space to z at p. They are the same. So together they do not generate this full tangent space to n at p. This captures the fact that m and n intersect with some kind of multiplicity. They share some common tangent direction. If the inclusion map from m into n is transversal to z, we also say that m and z are transversal, and we write it this way. Clearly, if m and z are transversal, then z and m are transversal. This is symmetric.